In this video lecture, we will be determining the sum of angles identity for sine and cosine. To start, we created two triangles within a circle of radius 1. Right here is our radius of 1, and then we have the green dotted circle. The first triangle highlighted is gray, and the hypotenuse is the radius. So our radius is 1 again. This triangle contains the angle A. So then its two legs have length sine of A, right here, and then it also has cosine of A, right there. The second triangle highlighted is green, and this triangle contains angle B, right here, next to angle A, and the length of this hypotenuse is the same as one of the legs from our gray triangle, specifically cosine of A. So this is a shared length. This means that the legs of the green triangle need to be scaled down by a cosine of A, resulting in legs of length cosine of A sine B right here. And then we also have the cosine of A cosine of B. Now we are interested in the blue triangle. This blue triangle is right here, and the triangle contains the angle A and B, angle A and angle B. And therefore it has leg lengths of sine of A plus B, and then also cosine of A plus B. For now, we want to focus just on the sine of A plus B, which is highlighted in lime green. In order to find its identity, we must figure out a way to rewrite sine of A plus B. Do you see a way to rewrite this? Here's a hint. Look for similar triangles.
There are many similar triangles contained in this image, but for now, we're going to focus on these three. Before we move on, let's discuss how these three triangles are similar. Looking at the yellow triangle, we see that it has a 90-degree angle and contains this angle B. A new angle is introduced in this triangle, and that is going to be what we call angle C. Together, the 90-degree angle, angle B, and angle C make up our yellow triangle. As you can see, we constructed parallel lines, a line parallel to JK through this point L. Looking at the orange triangle now, we see that there are vertical angles that exist with this angle C. So these two angles are equal, and that is because they're split by this transversal JL. Using the same parallel lines, we can conclude that the 90-degree angle in the yellow triangle is congruent to this 90-degree angle in our orange triangle because they are alternate interior angles. Through similar reasoning, angle B in the yellow triangle is congruent to the remaining angle in the orange triangle. And again, that is because they are alternate interior angles. Therefore, by angle, 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 the yellow triangle and the orange triangle are similar. Now we need to show that the orange triangle is similar to the purple triangle. Since this lime green line, sine of A plus B, is a straight line, we know that the angles lying on this line must add up to be 180 degrees. Since the 90-degree angle in the orange triangle lies on this line, the angle that corresponds to that in the purple triangle must also be 90 degrees, since those are supplementary. Now, some of you may have noticed that angles B and C are complementary, meaning that their sum is 90 degrees. Why is this true? This is true because the angles in a triangle must add up to be 180 degrees. Since the orange triangle and also the yellow triangle contain a 90-degree angle, the remaining two angles, B and C, must add up to be 90 degrees. Therefore, B and C are complementary angles. Now looking at this one red triangle, we see that it contains a 90-degree angle at this point L. Since the red triangle contains angle C from the orange triangle, and it has this 90-degree angle at L, we can conclude that the remaining angle of the red triangle is angle B. Now if we take the red triangle away, we see that the angle B of the red triangle is also angle B for the purple triangle. Therefore, this top angle up here is angle B. Ultimately, this means that the remaining angle is angle C, since B and this remaining angle have to add up to be 90 degrees. Therefore, by angle, 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 the orange triangle and the purple triangle are similar. And by transitivity, the yellow triangle is similar to the purple triangle. So all three of these triangles are similar triangles.
Do you see how one side of each of these triangles lines up with the side sine A plus B? Therefore, we can write sine A plus B as the sum of the sides of these three similar triangles. Looking at the legs of the orange and yellow triangles that lie on the line sine A plus B, we see that they're equal to the leg of our original green triangle. Right here. Therefore, the sum of the legs of the orange and yellow triangles is equal to cosine A sine B. The hypotenuse of the purple triangle is sine of A. We know this from our original gray triangle. This means that the length of the leg of the purple triangle that lies on the lime green line needs to be scaled down by sine of A. So its length is sine A cosine B. Some of you may have found that the length of this leg is sine A sine C, but since C is the complement of B, the sine of the complement is the cosine of the complementary angle B. So sine C is equal to cosine of B, therefore leaving us with sine A cosine B.
Therefore, we can write the sine of A plus B, which is this green line segment, as the sum of the sides of these three triangles, which are the cosine of A and the sine of B, but also the sine of A and the cosine of B. Ultimately, sine of A plus B will be equal to the cosine of A sine of B plus the sine of A cosine of B. Therefore, this is the length of our green line segment. Going back to our blue triangle containing angle A plus B, which can be shown right here, we will focus on the other leg length. Previously, we were looking at this long leg length of this triangle, which was the sine of A plus B. But now we want to focus on this lime segment here of the other leg side, that is cosine of A plus B. Similar to what we did with the sine identity, we want to find a way to rewrite cosine of A plus B. Can you find a way we can rewrite this? Here's a hint. Consider the leg lengths that you already know.
Going back to our original green triangle, shown here, we see that its base leg, which is also the line JK, is cosine A cosine B. We also see that this base leg, the line RL, of our purple triangle is sine of A sine B. From the diagram, you can see that sine A sine B plus the segment that we're looking for, cosine A plus B, is equal to the line JK, which is cosine A cosine B. Since we want to solve for cosine A plus B, through algebraic manipulation, we know that cosine of A plus B is equal to cosine A cosine B, this long segment, minus sine A sine B. Some of you might be wondering about the difference of angles. To find this, we're going to use our knowledge of odd and even functions. Since sine is an odd function, the sine of negative a is equal to negative sine of a. And since cosine is an even function, cosine of negative a is just equal to cosine of a. Therefore, using the identities that we found before, sine of a minus b is sine of a cosine b minus cosine a sine of b, and cosine of a minus b is cosine a cosine b plus sine a sine b.